So there are two major components of DataMed. I was going to talk about the front end and some of the other tooling around what you see on the online version when you go to datamed.org. I'll talk briefly about sort of the back-end indexing and processing framework and the current status. And this is our overall diagram of the full system, and again, I'll be talking about the areas on the top right. And really, the system, as it's designed, provides the ability for us to define a pipeline of processing of the metadata that we extract from various repositories, as Lucilla mentioned. There are three areas where we did a lot of work in the last year, and that was in terms of developing new ways to extract metadata from new repositories that we were interacting with, improving the mapping of the metadata to DATs, and also feeding back from what we're getting to repositories to Susanna's group, who is developing DATs. So there was a lot of interaction this year also in terms of looking what we're getting from repositories, looking at what's in DATs, and then working to improve DATs for the latest releases. And then there was also a lot of work in terms of how do we actually process the metadata. So we do pull in records from various different repositories. What are the ways that we can actually enhance or extend that metadata? And so there are a couple pilot projects and some other related work that we did to pull in some additional metadata. And I'll talk about each of these as I sort of go through the various pieces. And so first on the metadata transport, as people probably remember, there's a number of different transport mechanisms that we've developed. These are all basically stored in GitHub. So basically the system pulls this information from GitHub, and all the incoming metadata is converted to JSON. In terms of sort of a status, in terms of what types of ways that we're actually pulling metadata, the most common way is through web services from repositories. We have a couple places where we connect to databases. We also use some common standards that are out there for providing metadata. So OAI PMH, the Open Access Archive Initiative, provides an interface that some repositories use. Things such as direct download of the data via rsync, FTP, and Aspera as well. So, there are a number of mechanisms that have been developed over the course of the project in terms of how we're pulling data. And then there are actually some more complex ways that we have to pull data. So some sites, allow us to sort of get a listing of data sets and then through sort of a more expansive API, pull more detailed records. So, for example, George's ICPSR has some very detailed records, metadata that one can get, and so this is a two-stage ingester that we've developed for resources such as that. In terms of getting metadata, we've also been working with one of our collaborators, Cedar, in terms of developing templates within the Cedar system that align with DATS. So the latest template has been updated to the latest version of DATS, and this allows people to enter metadata within Cedar, and we're now discussing with Cedar potential ways, for example, with the Commons pilots, that people could potentially enter information about their data that they've uploaded into the Commons through a Cedar template that we can then pull in from Cedar and make searchable through BioCaddy. So this is one of these cross-project interactions that we've been working on in this last year, and we actually have a pretty tight collaboration with Cedar as a core development team has some regular meetings with them. In terms of metadata transformations, this is again, just a little updated, or not update, but sort of overview of how we're doing this. So we have a transformation language that we use to actually do the transformation. So we get metadata. Again, repositories, there are a few repositories that are actually providing DATS, but most of them do not provide DATS yet. And so, we have to do a transformation of that information into a DATS compliant model. And so we have a language that allows us to do these transformations. And as we bring in new data resources, sometimes the language has to be extended a bit. So that's sort of ongoing, work that's been going on in the last year as well. As I said, these transformations are stored in GitHub, so they're accessible. Currently, the pipeline is in an open GitHub repository that's publicly available. The data transformations are being cleaned right now because we put a lot of incoming data and information there, so we want to make sure that we don't have any passwords or anything else lurking on the data side, and that will also be made then a public repository. That's sort of in process. And the ingestion pipeline, one of the things it does, it will go through a data source to begin with and will generate sample data for a curator to work with, who then can define this transformation. Again, if we have information already in DATS, we don't need any of this, but for non-DATS services, we do need to provide that transformation. There have been a lot of sort of collaborations across BioCaddy that pull into the ingestion pipeline. So, accessibility metadata, Workgroup 7, has been something that has been incorporated into the curation process. And again, this is something that not a lot of repositories specify in the metadata they provide. So there is sort of some areas of the metadata that have been marked as important that are in DATS but aren't in standard metadata that one gets from repositories. So usually the repository will give you metadata about the data set that's being referred to, but doesn't give you all the details about what does it take to actually access that data set. And that's an important thing if someone is trying to find a data set they can use, right? Because they need to know what type of access restrictions there are. So George, had worked through, with his working group, a number of things regarding the accessibility metadata, and so that's now part of the standard curation process that happens when we actually bring in a new data resource. Let's see. So in terms of metadata statistics, this is taken from a run-through sort of the full set of metadata when we had 58 sources a little while ago, earlier this year. And just to get sort of an overview in terms of what the sort of size of records are and sort of what the variation is. And so at that time we were already 3 times the size of PubMed. So PubMed is order of 22 million or so articles. At that point we were at 77 million. And the average record size is actually not too big, but we do have a very large sort of range in terms of order of magnitude, in terms of the amount of metadata that's brought in, from each repository, from half kilobyte all the way to multiple megabytes, per metadata record. And so it really depends on the type of resource you're looking at in terms of the amount of detail that's provided in the metadata records. And so for certain metadata records, we might actually want to enhance those. The first one that was incorporated this year was developed by Hua's group at UT Health, and that's a natural language processing entity recognition module. And so what this will do, it goes into the data record, the metadata records, and sort of examines the abstract title, other fields, and then extracts relevant entities from known terminologies such as mesh and others, and actually then labels them using standard terminology, standard identifiers within the metadata record. So what happens for all these enhancements is that as the metadata record flows through the metadata pipeline, after the initial mapping, we then step through a number of different enhancement modules, and so we can define as many as needed. Currently, these are the 4 primary ones we're running, which is NLP enhancement is the first one. So basically takes a record and then writes information back into that same record. There's information on primary publication. So there are a number of data resources and projects. There's a pilot project that has information on primary publications, so to be able to write that information back. Data citation. So not the repositories themselves don't always have all the information about where a data set was cited. And with the new data citation work, it's also going to be existing in other places such as Crossref and DataCite, where one has these then data mentions listed. And so this module basically aggregates from the sources we have access to right now information on citation of the data, so that we have a better record of who is actually using the data. And then one of the latest one is built off the deployed work that has been done in this last year, and that's to look at some of the sort of aggregated analytics or statistics about data that might exist. So in this case, distributions of race, in terms of the data set itself, and having that as a module. And so I think Paul might have a screenshot of this as one of the new features. But basically, we have now this enhancement module that allows us to take in any well-structured sort of analyzed information about data sets in a repository and attach that to the record. And so again, we did this first with the deployed data, but basically any other type of analytic that we want that can produce the same or similar structured output, we can now write back into the record fairly easily. And then in terms of the document preparation, once a document is finalized, we then go on to the next step, which is export. But in terms of the overall document preparation, we've done over the last year also some tests, looking at what is the processing speed. And so with sort of average size data sets on a lightweight node, we're able to process about 20,000 documents per hour, and this includes some of the enhancement modules. And so this is, again, there's some metadata records, the very large ones, where the NLP becomes slower on those modules because it has a lot more text to run through, and NLP can be expensive. But this is sort of just an overview of some of the sort of the average data sets we're talking about. When we look at just the pipeline components, and this is the core pipeline. So basically getting a document, running through, the standard transformations, writing the document back to the data store, sort of getting a feel for how, that process scales from the large data sets. So Tremble is the largest data set we have. This seems to be fairly linear, and here we're actually doing 224 documents per second. So this is the core backbone architecture of the system. So, taking, discounting some of the heavy computation for the NLP. So this shows that the system is fairly responsive in terms of, being able to do the core processing. And then we can also scale the system. So we've also done some tests looking at, this was also looking at, doing a install on Amazon, because a lot of the, cloud work now, and NIH is looking at other clouds. So we have an instance up in Amazon that we've been testing. And reason for that is also because we wanted to make sure, some of the configuration issues, and so, looking at, how we have to configure Mongo and other things in Amazon, to make sure that we have a well-performing system. And what we did here is we basically ran a large data set, and then approximately every hour or so, we basically spawned, another computing node. So basically the system is designed that as documents are passing through to being processed, the messaging architecture allows those messages to be fetched from any number of nodes that are subscribing, to that message queue. So basically we can scale this to, a large number of nodes, to process these messages. And, again, we don't have, all the money in the world to run, hundreds and hundreds of nodes on Amazon. But, our small scale test, to begin with, showing that we got, very good performance gains, as we sort of, scaled up, the the number of nodes, through this test. So I think that is the last slide. Other than the export, we're still exporting to Elasticsearch, and I think that is it. So I don't know if there are any questions, or we want to go directly to Hua and.
Maybe Hua will cover this.
Okay.
The enhanced methodology.
Mm-hmm.
How is that certain?
So the enhanced metadata rights. So the question. Repeat the question. So Ian asked, how is the enhanced metadata searchable? And so the enhanced metadata is written back into specific locations of the metadata record that gets indexed by Elasticsearch, and then the application itself queries those fields. So the NLP data is actually put in a separate section and formatted and in a way for the identifiers and all to be there, and then that's queried by the application directly in terms of how the query is formulated. I think I kept us on time.
Okay. So I'm Hua Shu from UT Health, and Jeff and I actually co-lead the CD core development team. So I briefly actually give an overview of the update about the development on DataMed, the current status, and what we're going to do next. So my talk will cover several aspects, just reinforcement about the roles and the roadmap for the CD team. Then for the DataMed, I'll have a general architecture. Then, like Jeff said, he has talked about the data ingestion. I'm going to more focus on the search engine, and I'll spend some time actually highlighting some new features of DataMed version number 3, and then I have one slide about next step. So the role of the CDT is to develop the functional prototype DataMed, and we also implement guidelines suggested by the working groups, and we integrate systems modules developed by the pilot project and the supplements, and the last one is we actually engage end users into the DataMed development and evaluation. And this is a roadmap we have been showing many times, and right now we are actually here. We just released the version number 3 for the DataMed, and this is a sort of summary of the accomplishment since our last all-hands meeting. So we released 3 different versions of DataMed, 1.5, 2.0, and now the version 3.0. And on the ingestion part, we have included 74 data repositories and implemented the DATS version 2.2 metadata model for those data repositories, and also have enhanced the module for indexing like the NLP-based approach. And on the search engine side, we keep developing the NLP service, the terminology service, optimize the Elasticsearch ranking algorithms, and we add a lot of other functionalities I'll show you in the later screens. On the evaluation side, we created the data benchmark data set. We finished the data retrieval challenge, and also still working on user survey and the user studies. This is the overall architecture of DataMed, and Jeff already introduced the ingestion part on the top right corner, and I'm actually going to talk more about the search engine part, which involves the terminology, NLP service, and the user interface. So this is a simple MVC model for building the search engine. I'm not spending much time here. This is the workflow for the search engine on from the workflow aspect. So we start with the user query. We do NLP, actually recognize concept in those queries, and we look into the terminology server, find the synonyms of those concepts, trying to expand the query. and then we generally refine the query, send to the Elect search engine, and it goes find the ranked relevant results and rank them. We also show different facets. I think a lot of you already know the customized facets that are returned by the DataMed. And the user can refine through those clicking different facets and or looking into the data sets, then refine the query, actually redo the search again. And a brief introduction about the NLP server. So the goal is to leverage natural language processing approach to extract a biomedical concept. And we actually right now extract several specific type of entities, general biomedical concept to mesh, and specific like a disease, chemical, gene, biological process, and the cell line. We have individual NLP component actually recognize those entities. And the use of NLP both on the expanding the user queries, also at the ingestion process, we index the metadata texture fields. And the implementation of NLP tool is really a mixture of existing tools available in the community as well as our locally developed tools, mix both like a machine learning based named entity recognition system plus rule-based systems, and other existing tools like MetaMap also used here. So this is a small evaluation on the how good we are recognize those different type of entities like a gene, disease. So we actually optimize our system a little bit. We focus on high precision. That means we want to make sure whatever we recognize is more accurate. We may miss some, but whatever we recognize is more accurate. So you see the first number of precision is close to 90%, or some of them are over 90%. And we also actually did the evaluation because we are writing the JAMA paper recently, and one question is also what's exactly the effect of the NLP-based approach on querying on retrieval performance. So using the benchmark data set we created for the data retrieval challenge, we actually looked without expanding the query using NLP versus using NLP to expand the query. The difference is actually quite big. And with the expansion, actually, we can reach inferred average precision like a 0.2033, and the P10 is also close to 0.6. So on the terminology side, it's been, we pretty much established the terminology server. The idea is to leverage existing terminology in the biomedical domain to facilitate the search. And it has been used for multiple places. We expand the term to find the synonyms while you're doing the indexing, as well as for the query expansion. And recently we re-implement the auto-completion when you're doing the search, and you can try it out, and also collect the spelling errors when you're doing the search. And this is some little bit details about implementation of the terminology server. We collect a few reliable terminologies and implement into the Neo4j geographic databases using SiteGraph to interface with the database. And in terms of the ranking algorithm, recently we actually updated the default. We used to use the default Elect search algorithm, but now we actually use the Elect implementation of a probabilistic model called GM25, and a lot of more work actually doing on the ranking because we have two pilot projects from Emory, from UIUC. We actually have more algorithm developed through the data retrieval challenge, and we actually going to implement those more advanced ranking algorithm into the DataMed in the next couple of months. And then next few slides, I'm focused on several highlights about the new features of DataMed, all of which you can actually just go to the website and try it out. So I'll highlight a little bit about what's the current status of the data, then talk about the web API. We have made it available online. Then the fine-grained user tracking system we have been implemented in the backend, and the reporting of the broken link, how we detect the duplicate data sets, And visualization, the data statics, the deployed project, which I'm not going to talk much because we have a talk in the afternoon about this project. And also schema.org markup. Basically, we made all those alignment to schema.org. So other search engine like Google, they can actually more easily find what we index. And if people search Google to find a data set, they may actually find a page from DataMed. So this is the current status. Actually, I think Lucille already showed this page. I just want to point it out. Right now we have about 2.3 million of data sets in the current DataMed. And this is a screenshot about the web API. If you want, you actually go to try it right now. So if you go to DataMed, on the top bar, there is called the web API tab. You can click that, and you actually will see this page. So basically, this is provide a way for you for other systems to want to integrate with DataMed. They can submit the request through this API, query DataMed, find the relevant records, and send it back. So potentially, this will provide an easy way for other systems to sort of communicate with DataMed. And you can actually test it out here. Basically, you can select one of those query. What do you want to find? Then type. Maybe I can demo a little bit, or I'll demo later after. Can I exit this? Actually, okay.
You want to demo right now?
Yeah, just for this function.
Okay.
I think if people are interested. Why it's so slow? Are we connected? Oh, okay. Thank you. I don't know why it's so slow. So this is the interface actually you just see from the screenshot. And there are 3 different ways to query data set, either by data repository or specific data type, or actually find the specific data sets. So if you say you try this, sorry, not very good on this Windows machine. Trying to move the bar a little bit. Or I think I can click this. Try it out. And oh, I didn't import the keywords. Sorry. Hold on one sec. Really having some difficulty actually. I try to move the text a little bit. Click try it out. You enter a query term here. Whatever. Press cancel. Then you can select database here. But if you don't select database, it's basically search everything.
So when you enter a keyword there, is it just doing a text search, or is it using your pre-ingested?
Yeah, it's pre-ingest everything. It basically just like you searching on DataMed. But this is basically showing you can submit what data DataMed can return as an electronic format, and you can actually then pass this out, put this actually into your own website or something like that. So this is basically showing how you can consume like a DataMed as a web service.
Right.
So that's.
Is it using SiteGraph on the back end, so that if, for example, if I did a search?
SiteGraph, yeah. When you expanding, looking for you find the term, you find the concept using NLP. Then you try to find the synonyms using SiteGraph, that interface, because the terminology is maintained in the SiteGraph database. And see, this is what it will return. So your program can actually take this returned XML or JSON and pass it out and do whatever you want, display on your own website or whatever you want to do on your site. So, all right. How do I get back to the slides? But you can just try it out online, that's why. All right. Thank you. So this is about the web API, and I think we are very looking forward to people to try it out and give us feedback. And this is about the user tracking system. So what we do, we want to use this to facilitate user studies. We also want to know what exactly people are using the DataMed. So on the back end, every time when people do a search, we will record the search term, of course, the query term they have been entered. And then we actually will record whatever returned by DataMed, and we'll record what did the user actually select, what they picked. They think it's relevant or they want to take a look into it. So basically every single click the user do, like even they click the facets, we will record what they clicked. So basically all the workflow the user did, we most likely will collect all those information. And this is very useful. We can do query log analysis, and it's also facilitate our usability study. And we also have some information about most accessed data, things like that. And also by looking at what users think is relevant, or they take a look, that's kind of like a user feedback about the relevance. So we can further use to improve the ranking algorithm. So this is the thing actually currently implement in the DataMed, and we can easily switch it on or versus off if there's a kind of a traffic issue, because it actually records a lot of things. Broken links. So we actually receive a number of reports actually when people go to the original website, the link is broken. You cannot find it. So we actually develop a way. We automatically screen all the links we have with the original to the original website. And once if we found some broken link, we will actually get notice, and we will actually highlight right over here, say this link is broken for the user. But it's actually basically also good for us to know, so we can actually do some update and how to fix this broken link. And the next feature is about the duplicate data sets. I think this one will also spend quite some time with Jeff's team, how to represent those duplicate data sets. In this case, actually, basically, you search this term, actually find 3 data sets, they actually duplicate. So we will have one data set as a primary data set, and the other 2 is like a secondary data set or something. So if this is a primary data set, there is a button, it says View Secondary Data Set. So you click this button, you will actually expand. It lists the other 2 data sets as a secondary data set, which have a reference to the primary data set. And on the next one, it will actually say over here, it says View Primary Data Set, because this is a secondary data set. So you can actually link among those 3 data sets, they actually the same. So this is a duplicate data sets. So, and this is, I'm showing a brief user statistic. We just logging did it the day before yesterday. So up to now, this is about a year data based on Google Analytics. Up to now, we had about 11,600 users ever used DataMed, and of which about 1/3 are recurrent user, and 2/3 are new users. And they also have some data about like a average page they viewed, about 4 page, average time they spend on DataMed, like 3 minutes, something. So this is a data about from last year to now, about a year. So I don't know if this tell us much, but at least we get some idea, like how many people actually ever access the DataMed. Go ahead. I'm actually not quite sure. This is actually all done by Google Analytics. They probably track the IP address or something like that. so they can know if this user has previously been in this site based on IP or something. I guess it's maybe, I don't know, I just guess. If it's like in Google, they have a way to track the user's IP or some kind of ID, MAC ID of a machine. If they see it's a new one, then they define as a new user. If it's matched with one existing, they define as a existing user. So that part I'm not quite sure, but. Yeah, we also have registered user, which I don't have the number, how many registered users we have. We have the user register function. They can register either using NCBI, is it NCBI account? The Google account, at least. And we also talked about at least using the NCBI account or other kind of NIH account they can log in. In terms of just a summarization of publications since last year, so we have a number of papers. I think this is first one is published, the second one and the third one are two papers from the data retrieval challenge. One is accepted, one is review, led by Kirk. He's here. And we also have two more papers. One is about DataMed, actually architecture technology paper is under review at the JMIA, and the other one is about the user study. It's also under review for the JMIA special issue. And in terms of abstract presentation, we have present at AMIA, at the ICBO, BD2K all hands meeting, and we also have two more presentations coming up in the 2017 AMIA conference. Next step, so we are thinking about still, because the last time I think sometime we mentioned about 100 repository, and we think we're still towards that goal. Hopefully we can reach 100, and with DAT 2.2, and develop automated tools for data ingestion. And actually I should say the other things is also about ingestion, because for example on the deep search part. Anyway, ranking algorithm, we're going to implement more advanced algorithms from those pilot projects. But we also talked about more deeper search, which actually involve both the ingestion and search engine. For example, we're talking about how we can search the study variables based on the common data element, CDE. That's actually something big. Then we also talk about how we can see the data statistics by integrate other things like count everything and the other projects. And a bunch of new functions still on our list, and the evaluation will keep going on. Given that, I'd like to thank all the CDT members and NIH for this great opportunity to do this kind of research. And thanks everyone, and any questions?